Hello everybody. This week's lab is going to be pretty similar to last week's in that you guys are going to see a bunch of pictures and you're going to be asked to write down the measurements that those represent. And then we're going to use those measurements to do a few different calculations. So in the first scenario here, we're going to measure the length and width of a rectangular piece of paper, and then we're going to measure the diameter of a circular piece of paper. And what you're going to be asked to do is to calculate the area. The area of our rectangular piece of paper is pretty simply just the length multiplied by the width. Our length has units of centimeters. Our width also has units of centimeters, so we're not going to have to make any conversions there. And ultimately, we're going to have centimeters times centimeters, and we're going to have our area with units of centimeters cubed or squared. Then we're going to be asked to measure the perimeter. The perimeter is the distance all the way around our rectangular sheet of paper. So we can see it's going to be this distance plus this distance plus this distance plus this distance, or 2 L's plus 2 W's. Next, we're going to move on to the circle, and the circle is a little trickier because we're given the area in terms of the radius, but the radius of a circle is pretty difficult to measure actually. Determining what this middle point exactly isn't really very easy or practical. So typically you're going to see this measurement as a diameter, the distance all the way across the circle, which is a little easier to get at. So the first thing they're going to ask is, what is the radius? And we know that the diameter is going to be 2 times the radius, therefore the radius is 1/2 of the diameter. Knowing this radius, we can now calculate the area as simply pi r squared. But I do want to point out that we could also make a substitution here. We could say that this radius is equal to 1/2 the diameter. Plug that into our equation for r here. And now we're going to be squaring the diameter, and we're going to square 1/2. 1/2 squared is 1/4. And then we get 1/4 pi d squared. And we can plug our original diameter measurement in and still get at the area. Similarly, we can do the circumference as 2 times pi times r, or if we made our substitution, we'd see that it's simply pi times the diameter. And the circumference is to the circle the same as the perimeter is to the rectangle. It is just the distance all the way around that circle. In the next portion of the lab, called calculating volumes of 3D shapes, we're going to be given one of these 4 shapes to have measurements about here. So it could be a cube, it could be some kind of generic block shape, it could be a sphere, or it could be a cylinder. And in the case of the cube, we're going to calculate the volume as this length here, cubed, or L times L times L. And we're going to have our measurements done in centimeters. So if we do this up, we're going to see that we get units of centimeters cubed here. Here, in a generic form, where the distances are not all the same like in a cube, we have the width times the length times the height. We'll multiply all those together, and we will still get centimeters cubed for the volume of that. Circles are again spheres are a little trickier than the cube or the block. In this case, again, we have a very difficult radius to measure. How are we going to get and measure to the center of the sphere outward? That wouldn't really be practical. So we're going to get the diameter, the distance all the way across it. The radius in this case is again 1/2 the diameter. The volume of a sphere is 4/3 pi r cubed. If we were to plug in our definition for the diameter here, we would get 1/2 d cubed. If we did that math here, 1/2 times 1/2 times 1/2 is 1/8. We get d cubed here. We combine these two together to get 4/24 pi d cubed. If we reduce this fraction by dividing both the numerator and the denominator by 4, we're going to get 1/6 pi d cubed. For the cylinder, the volume of the cylinder is the area of this circle multiplied by the height of the cylinder. We again have the fact that this is difficult to measure, so we're going to get a diameter. We have that the radius is 1/2 the diameter. Our volume given to us is pi r squared times h. Remember that pi r squared was our area of the circle previously, and we've already seen that there is equal to 1/4 pi d squared. We'll multiply that by h, and we can get the volume of our cylinder. So just like we did massing by difference before, we're going to be measuring volume by displacement, which is very similar to our massing by difference. We're going to measure the volume of a water initially. We're going to place something into it. It's going to displace some of that water, make it go higher, right? You could imagine putting like a bunch of marbles in a cup of water. It's going to cause the water level to rise in the cup. So in this scenario, our known variables, we're going to have the mass of the beaker before we've added these aluminum pellets. And then we're going to add the pellets in there. And so this beaker has some water in it. So this is water and beaker mass. And then we're going to add some pellets to it. And we're going to mass it again. We're going to know the volume of the water that we started with, and then we're going to know the volume of the water once we've added the pellets. The question is, what is the mass of the pellets? What is the volume of the pellets? And what is the density of those pellets? So the mass is pretty simple. This is our massing by difference that we saw last week. So the mass of the pellets is going to be the mass of the beaker and the pellets minus the mass of the beaker. The volume of the pellets is calculated very similarly. The volume of the pellets is going to equal the volume of the water and the pellets minus the volume of the water. Finally, we can calculate density. We'll remember that density is mass divided by volume. So we'll take the mass of the pellets that we've calculated here, and we'll divide that by the volume of the pellets that we calculated here. Finally, we're going to be determining the thickness of the aluminum foil sample that we have. So our known variables, we're going to have the mass of the aluminum foil. This is something that we measured. We're going to have the width of the aluminum foil. We're going to have the length of the aluminum foil. And we're going to need one more piece of information. This is the density of aluminum that we determined in the last part. So this is a calculated value, and these three are measurements. And we're going to be asked, what is the volume of that aluminum foil? And then what is the height of the aluminum foil, or the thickness of the aluminum foil? So the volume of the aluminum foil we're going to get from our density equation by solving it for volume. So the volume of the aluminum foil is going to equal the mass of the aluminum foil divided by the density of aluminum. And then finally, for the thickness of the aluminum foil, we're going to remember that volume in this case, as we just saw, is width times length times height. We know the width and the length, but we want to know the height. We just calculated the volume, and so solving for that height, we can see that it is the volume of the aluminum foil divided by the width of the aluminum foil times the length of the aluminum foil.